Welcome back to eCoreAcademy, everyone. My name is Anita Raj, and I am one of the co-founders here along with my younger brother, AJ Raj. Today we have a new Algebra 2 lesson in which we'll be wrapping up the polynomials unit. Of course, hopefully you expected it, but we're going to be doing polynomial applications, where I'll be showing you some real-world scenarios where you'll be seeing these kinds of problems. In the last video, we also did something similar, but in this case, these are problems that are things that you might see on assessments because these problems involve things like boxes, volumes, dimensions, dimensional analysis, and then you'll also have problems where you're given a set of numbers that you don't know, but you're given their relations to one another, like this number is 3 greater than this number is 2 less than this number, etc., etc. So relations between numbers, things like that. And you might be thinking, how do these different math concepts, math problems connect to polynomials? And that's exactly the point of the video today. How can we use polynomials and the techniques we know, like finding zeros, understanding what a polynomial looks like on a graph, etc., to solve these problems that might not seem like they use polynomials? So we're going to look at some problems involving simple problems with boxes and more. And before we get into the video, I'd really appreciate it if you all could like, subscribe, hit the post notification bell, comment down below, and share using our socials. Thank you. So let's jump right into the first problem. Here's actually a picture of it straight from my notes. This is the problem, and then this is the work that I already did on paper ahead of time. So let's just read the problem. Nancy has a piece of tin 14 centimeters wide and 18 centimeters long, so it's a rectangle. She wants to make an open box with a volume of 180 centimeters cubed by cutting out a square of the same size from each corner and folding up the edges of the piece of tin. So right now we have a 2-dimensional flat tin rectangle, and what she wants to do is by cutting out the corners, if you realize that if you fold up the sides, you can actually make a box. It just won't have a lid to it, which is what she wants. She just doesn't want something to cover the box, just an open box. And we can do that by cutting out the corners as shown in this picture and then folding up the edges. She wants to cut out a square of the same size from each corner and fold up the edges of the piece of tin. To the nearest tenth of a centimeter, find the length of a side of the square that is cut from each box. So I think I showed you here in this picture, but we're trying to find the edge of the box, the edge of the square that she's cutting from the corner of the box. And she's cutting from the 4 corners because it's a rectangle, 4 corners. And we're just trying to find the side length of that corner. So I think we're going to just jump right into it. And I'm going to clear this off my screen so that I can actually do the work with you. So hopefully you got a look at the problem and we're going to work through it together. So I'm going to first draw the rectangle, which was the piece of tin, but I'm going to draw it with the squares cut out from the sides. So here is one side. Here's another side. Here's another side. And then here's the last side. And then I'm just going to draw dotted lines to represent the squares we're cutting from the corners. Because if you look at these dotted lines, they actually create a rectangle with the shape we created here. But if we cut those out, we have these squares right here. And we're going to assume these are all the same size. They're all similar. They're all equal. So what we're going to do next is, if you look at this side here, it was originally 14 centimeters long. However, if we call this side of the square x and we call this side of the square x, the new length of this side is going to be the 14 centimeters minus 2x because we're removing the 2 squares from both of these corners. And the same applies to this side. Let's assume this is the 18 centimeter long side. It was originally 18 centimeters, but if we call this side of the square x and this side of the square x, because remember, it's a square, all sides are equal, we're also removing 2 x's from this side of the box. So these are the new dimensions of the shape we're looking at. And then now we're going to have to do some imagining. If we have this flat shape and we're folding up the edges, this side right here is going to be equal to the height of our open box. So if we fold up the edges, this side right here, which is technically x, which is technically the edge of the box, is going to be the height of the box. So next what we want to do is we want to develop some equations for ourselves. We're being told that Nancy wants a box with a volume of 180 centimeters cubed. So we're going to make y equal to the volume of the box. Remember, y is equal, typically when you're dealing with something like a 3-dimensional shape like this, like in this case, it would be like a rectangular prism. Volume is equal to length times height times width. So in this case, we want that volume to be equal to 180. And I'm not going to put units, but it's 180 centimeters cubed. That's what the problem stated. So now we have to come up with another equation, because what we can do is we can develop another equation. This one will be a polynomial. We can put these in our calculator, find their point of intersection, and solve for x. So in this case, like I said, x is equal to the height and the question's asking to the nearest tenth of a centimeter, find the length of the side of the square. The length of the side of the square that we're cutting out is x. We also said that x is equal to the height. So in this case, instead of writing the volume as length times width times height, we can write it as length times width times x. And this is what we're going to do. So if we write that formula, length times width times height, we can fill in each of these values. So the length, let's just call the length 18 minus 2x. 18 minus 2x. The width is going to be the other side, which is 14 minus 2x. And then finally, the height, like I said, is equal to x, just the side of the square, times x. And that's your polynomial. You're going to put both of these in your calculator and find where they intersect. I'm not going to do that part with you, but hopefully you can figure out. And again, I want to remind you that height is equal to the side of the square. So height is equal to x. And then you should be able to find that length is going to be equal to 0.9 centimeters, or it might be equal to 4.8 centimeters, depending on what intersection point you find. And what this means exactly is that the polynomial 18 minus 2x, etc., is going to intersect with the line, the horizontal line, 182 times. So you're going to get two answers if you make sure you check all points of intersection. And that's how you solve that problem. And by length on that last side, I meant the length of the side of the square, because that's how the question phrased it. It said find the length of the side of the square. So again, that length, that L, is really just the height, which was equal to x. Here's the next problem. This looks like a little bit less work. The reason I included it is because there is some reasoning you're going to have to do. If you understand this reasoning, you can really just apply it to any kind of problem you might see like this. And I'll show you exactly how we would do this. So it's really just one sentence. Find 4 consecutive multiples of 3. Consecutive means they come right after each other. For example, consecutive numbers 1, 2, 3. They come right after each other. In this case, 4 consecutive multiples of 3. That would be 3, 6, 9, 12, just right after another. We're not skipping a multiple in between. Such that the product of the first, third, and fourth is 1,080. So in this case, we're looking at 4 different numbers because first, third, and fourth. In this case, the second is omitted, but we have to assume there is a second multiple because it says consecutive. We can't just skip over the second one. It just isn't included in this equation that they've given us in word form. So we're going to develop some equations based off of what we have here. And what we're going to do first, in this case, you have the first number, the first multiple, you have the second, which was not mentioned in the problem, but we cannot skip over it because it said consecutive multiples, so that means right after each other. And then we have the fourth. So what we can do in this case, the first we're going to assume is the smallest number, because if we're going by consecutive multiples of 3, we're going from the smallest multiple of 3 up to the largest. So 3, 6, 9, 12, etc. But we are not sure that those are the exact numbers, but that was just an example. So in that situation, 3, 6, 9, 12, 3 would be the smallest number, 3 would be the smallest multiple of 3, and that would be our first number. So x is going to be the smallest number, and x is going to actually be the first number in this sequence of consecutive numbers. First number. We're also told that the product of the first, third, and fourth numbers are going to be equal to 1,080. So we can actually create 2 equations based off that information. Y is going to be equal to the product. So again, the product in this case is 1,080. So y is going to represent our product. We can also write a polynomial to represent this product. We know that the first, third, and fourth are equal to 1,080. So I'm going to write x times, and remember x represents our first number, so we're just going to leave x by itself, times the third number. So the first number is going to be x. So what is the second number going to be? Well, if it's going to be a multiple of 3, isn't the second number just going to be 3 more than the first number? So in the case of 3, 6, 9, 12, if the first number was 3 and the second number was 6, isn't 6 just 3 greater than 3? And if you look at the third number, 9 is just 6 greater than 3. And that's how the pattern continues. So the second number is going to be x plus 3. The third number is going to be x plus 3 plus another 3, which is going to be x plus 6. And then the fourth number is going to be another 3, which is x plus 9. In this case, since we're omitting the second number in this product, we're going to skip right to the third number, which should be x plus 6. And then lastly, the fourth number, which should be x plus 9. And then if you plug this in your calculator and then find the points of intersection, you will solve for x. But be aware, when you solve for x, you only found the first number. And if you did this correctly, you should be able to get 6 if you do that in your calculator. And using x, using 6, you should be able to find out the other numbers because x is just equal to 6. So why can't you just plug it into all these other little equations we came up with? So if we're looking for the second number of x is equal to 6, 6 plus 3 should be equal to 9. 6 plus 6 should be equal to 12, and then 6 plus 9 should be equal to 15. So those should be your 4 numbers, and that would be how you found that. And then our last problem. If a 6-inch slice is cut from one face of a cube, so we have a cube, we're cutting off a piece of it, the remaining solid has a volume of 258 inches. To the nearest tenth of an inch, find the length of an edge of the original cube. So we had a cube, we're cutting off a slice of it. So think of like, I don't know, a cake, and you're just cutting straight down, you're cutting vertically, and you're just removing a piece of it. And let's pretend this is a rectangular cake, you're just removing a piece of it. We're being asked to find what was the original length of the cake. In this case, it's a cube, so we can think of a cube cake. But that's what we're trying to find. And then this is the diagram I drew. These are the equations I use another polynomial. Not much work because I put it into my calculator and I leverage my calculator as much as possible. So make sure you are using a calculator in these problems to do that additional math, that wrote just graphing, intersecting by yourself, because you should be able to do that. But I want to walk you through how do we derive these equations from these word problems. So let's actually go through this problem. I'm going to draw a cube, and excuse me if it's not too good, but I'm going to sketch a cube to represent the cube that we're working with in this problem. And the information we were given was that, just pretend this is a cube, all edges are equal in length, etc. We're being told that a 6-inch slice is cut from one face of the cube. So I'm just going to hash this side of the cube, pretend this is the section we are cutting off. So this is going to be the cut part. And like I said before, this is a cube. Each edge is the same. So the volume would be length times width times height, but in this case, the length, width, and height are equal to each other. So volume is just equal to, and if we call, let's say, the length equal to x, it's just x cubed, because this would technically be x times x times x if we made them all equal to each other, which they are in a cube. So the length is x, the width is x, the height is x. That's basic knowledge. However, what's happening is we're cutting off 6 inches from this side. So pretend this much was cut off. So pretend this was the 6 inches. So how do we account for that? Well, we're cutting off from the length. So we have to include a -6 here. The width isn't being affected. The height is not being affected. We're not cutting this way. So the only part being affected really is the length. So we include the -6 because we have to include the 6-inch part that was removed from the cube. Because the reason we're doing this is we were given the volume of the solid after that section was cut off. And the volume we were given was 258. So 258 centimeters cubed is not the volume of the solid before the original cube. That's not the volume of the original cube. It's the volume of the cube after that section was cut off. And because we have the volume of the cube after that section was cut off, we have to account for that. So the new volume here, and in this case y is equal to volume, would be the width, x, the height, x, times the length, which is going to be x minus 6 because that 6-inch piece was cut off. And if you plug these both into a calculator, find where they intersect, you will find that x, which was the length of the original cube, the side length, you will find that to be 9.1 inches. It looks like 91, sorry. That's 9.1 inches, and then that is your answer. So that's how you would solve this problem. A lot of these problems are really just, especially the volume ones, a lot of visualization. So what I do for these is I always draw them out if I can. Because, for example, drawing it out and seeing that the cut part is only going to affect the length of the cube, not the width or the height, will help you come up with an equation that will effectively help you come to the answer and find the side length of the cube. And that's all for today's lesson. I hope it was helpful. Please make sure to like, subscribe, hit the post notification bell, drop a comment down below, and share using our socials. Thank you for watching, and I hope you join me soon for more Algebra 2 videos. Bye!